So what is a biomarker? What is a biomarker of aging? So clearly when we talk about biomarkers, we can run the full spectrum from molecular to functional. So I'll just start off by asking this question to the panel. We'll start with maybe Vadim, go around to Keith and come back. And then we'll get into more specific details.
Yeah, this is actually a very good question because that's exactly the question that we kind of posed to the consortium, Biomarker of Aging Consortium, and maybe Mahdi could discuss a little bit more, but I will basically say that this consortium came up with the consensus that biomarker of aging is something that quantifies biological age at the level of the organism. If you're talking about biomarker of aging for the organism. We could talk biomarker of aging, of course, for tissues or for cells, then it would be, biological age of those particular living systems.
So basically, if I'm understanding you correctly, something that basically functions as a proxy for the age of the organism.
Yes, exactly, yeah. But maybe Mahdi could extend.
Yeah, I really like that question because after working on biomarkers of aging for a few years and talking to everyone else who works on that, we realize we don't have a good definition of that. So we spent around 3 months, almost full time, talking to everyone, at least 25 labs, and just asking everyone how you would define biomarkers of aging. And we got such a diverse response, so we realized that we should connect it to something else more fundamental. So together we defined biomarkers of aging as a quantitative parameter that measures biological age. And then we spend a few more months on defining biological age. So now we have another definition for biological age that measures anything, any measures that's age-dependent biological changes, including cellular and molecular damage. So this is the current state of consensus for our definition of biological age and biomarker of aging for the purpose of studying biomarkers in the context of longevity interventions. But I'm sure there's also a lot of criticism on that.
I would like to add that a good biomarker is one that is as causal as possible, that is, as closely connected to the mechanisms beneath. And one of the reasons we don't really have good biomarkers of aging is we don't fully understand those mechanisms. But we would like it to be so that we can test therapeutics with it without, if it's correlational, it might be that what we're looking at is something is protective against aging that you don't want to get rid of. And so we would like to understand the mechanism and use that to get our biomarkers.
Yeah, I think it's an interesting point that obviously we also want those biomarkers to, in a way, give us a better understanding of aging itself, right? Sure, it should measure biological age. They should change with age, but also like with interventions. And from there on, we could use those biomarkers and go back and find mechanisms. So I think it's like almost this back and forwards that we will have between biomarkers, intervention, biomarkers, biology, and thereby create this like cycle of innovation, hopefully.
Yeah, I agree with everything that's been said, but from my perspective, I like to broaden this definition out to include things that aren't just like biochemical, but physiological in nature, because things that sound simple, like how easily you can get up from a cross-like position without having to lean on something, are actually remarkably predictive for your future health span and lifespan. So I think it's very important to kind of add that into the mix as well, building upon everything that was said earlier.
Yeah, so that was an interesting point that was raised earlier about different biomarkers of aging and some, whether some are correlative or causative, right? So graying of hair, for example, is obviously correlative, but it's not a driver of aging per se, versus telomere attrition is correlative, but also in some ways causative of the senescence of some cells, and both can be considered to be biomarkers. And to Keith's point here, we've been hearing a lot of talks about biomarkers of aging, but specifically with a strong focus on the methylation status and the change of the methylation status, the change of the epigenetic status of the genome, with great work done by Steve Horvath and then applied at Vadim Gladysshev's lab. And there being a lot of mathematical and statistical rigor, so these clocks are becoming very accurate. So when people talk about biomarkers, a lot of time I think it's taken for granted that we're just talking about methylation clocks. So I'd like to open this up and ask people's opinions here on what other biomarkers of aging are there that are as robust and as accurate to detect or determine biological age as the methylation clocks that are out there. Or maybe they're not as good, or maybe maybe they're better, or maybe they're just as good. So what is out there that is as robust as the methylation clocks that are out there, or are those the best? So I'll start with Vadim here, and we can move around.
I would say that epigenetic clocks are the best so far. Steve does a great job here for all of us. But at the same time, I think in the future we need to move to multi-omic kind of level. So currently in our lab we try to combine both epigenetic and also transcriptomic clocks. So we develop a very good transcriptomic clock. Especially in the mouse models, we actually do both regularly. And it's actually a good test whether these completely orthogonal kind of measures, they correlate with one another. So, but then of course, you know, as mentioned, it's good also to use like digital biomarkers, so physiological, functional. It really depends on what you try to measure. So in fact, that's actually question is wrong question because it's not like which one is better. It just depends on, if you want mortality, maybe use GrimAge. Like GrimAge works really well also under stress conditions, so PhenoAge. If you want to quantify chronological age, maybe just clocks that trained based on chronological age. If you want to study rejuvenation, that's a completely different story. So it's a little bit hard to say what actually is the best in this particular case.
Yeah, so another thing that we spent time to agree together with a larger group is what are the current different types of biomarkers and what are different classes of biomarkers. So in the context of aging, with this group that we put together, we agreed that there are molecular versus physiological biomarkers. And under molecular, we have omic biomarkers that includes epigenetics, transcriptomics, metabolomics, proteomics, and all these different omics. And now we are in the process of comparing them. And for comparing them, we needed to define a way to measure their performance. And the easiest way was to measure how they predict mortality and other aging outcome. So the current effort is to compare different omic biomarkers, which are the most popular one for clinical trials, and see which one can better predict aging outcomes. And I also have a small announcement that we are hosting a biomarkers competition starting December, and everyone who is building biomarkers can apply their biomarkers and see if their biomarkers predict aging outcomes better than the existing biomarkers.
And it's going to be a prize associated with that.
Yeah, so far $100,000 prize pool for that, but we are also raising more, so if you want to support that.
Well, I agree that the methylation are the best ones, the epigenetic, because they contain the answer as to how species change lifespans. It's been shown, you know, even if it's just over a winter or if it's a worker bee becoming a queen bee. But if you want to get more causal about aging and get even better ones, I would include the multi-omic, and then I would also add on that AI is showing a capacity for finding causal relationships within multi-omics. And as that capacity increases, I think you'll be finding that that will be the best biomarker creator.
So I would generally agree that, like, as of now, methylation is making the race. But the thing is, it's also as like they're like the oldest aging biomarkers, or not the oldest, but like when Steve pioneered this field, right? They have a head start. The technology is better. It's like there's more standardization going on. Everybody's using roughly the same arrays like to measure methylation, right? So it's like transferable. Whereas a lot of other technologies that are currently being explored to build novel biomarkers, the standardization is not there, like, especially like in metabolomics, right? A lot of different labs have like their own routines. And that makes it tricky sometimes to compare those things, right? So there's even like technological issues that even if we can measure certain modalities of markers in the body, they're like just like not going well together yet. And I think that's like where we need to bring other technologists, not only software technologists that build better algorithms, but like even like hardware technologists in the space to enable like whole body gathering of every fluid, of every modality that is in the body, and then we can envision this future of like multi-omics clocks where like all the modalities going together, and we have like the AI that selects which is the best for measuring what, and then also allowing the interpretation of those things, because doctors and clinicians like that. They want to understand it better and not only just get a number output.
Yeah, I'm going to answer this question in a slightly cheating way, but in a way that I think is truthful, building off what Max was saying. I think the best clock maybe isn't yet, but will be a massively combination clock, right? That has an epigenetic component, that has a telomere component, that has a physiological component, right? Because I think, you know, if you're trying to put all your eggs into one basket, you might have overrepresentation or perturbation. If you have a clock that's sensitive to inflammation, if maybe I have some serious shock, it'll show my age going up by 20 years, right? Where it's overranking because it's kind of putting all those eggs in one basket. So what I'm very optimistic on is if we have more comprehensive, like full body diagnostics that can gather all different types of information, we'll be able to get a more robust clock. We're not there yet, but.
Maybe I'd like to, just to make one point, just stress, because we use word aging for completely different things, right? So for some people, as this conference also was clear, it's like age-related mortality. For some people, it's functional decline. Some other people, damage accumulation. That's completely different things. So of course, they relate to one another later in life, but in some ways they also, as also Steve's talk indicated, it's very clear that mortality is not like damage accumulation, for example. So then we say, what is the best biomarker of aging? Then we use a biomarker of what specifically? Depending on what we define by aging, then we develop biomarkers specifically for that manifestation or aging itself.
Yeah, so tying into that, so one of the well, there's a number of reasons why people are actively pursuing a variety of biomarkers of aging, and one of them is to expedite trials, right? You can't wait to see if your drug is going to make somebody live 150 years, or actually, you know, or you know, otherwise, yeah, it's highly impractical. So you want to have a proxy. So so the question I have is the various biomarkers that we're applying now, and maybe Steve can answer to that. Particularly the methylation clocks and perhaps other biochemical biomarkers, or perhaps even physiological biomarkers. If there's an intervention, if there's a trial that's using a drug or whatever the intervention is, and you want to see if it's generally having an effect on aging, on some sort of rolling back the clock, so to speak, do we know for certain, I guess maybe we don't, but do we know if some biomarkers are better for assessing whether or not that intervention is working? Can a particular biomarker miss, you know, could your methylation clock tell you that, well, you haven't actually rolled back the clock here, but maybe there is an effect on, you know, rolling back the clock on neurons, for example, versus another type of tissue. Or maybe your drug is having a beneficial effect on aging, but that particular biomarker isn't fully covering, you know, the changes. So would you need a panel of biomarkers, or do we know for certain that, you know, we have one biomarker that can basically do it all? For example, when we take a drug and see if it's actually reversing aging, right? Whatever, you know, across all tissues, across all, you know.
So to address these questions, we actually developed this biomarker of aging consortium because we need, as a community, to come with some sort of consensus, at least to develop guidelines how we can test biomarkers of aging. So we're currently, it's an open question. So, you know, perhaps the biomarker of aging that needs to be used does not exist yet, perhaps. So if we choose among the biomarkers currently available, I would choose probably GRIM-Age and GRIM-Age2. Steve's and PhenoAge is also good. So, but we, for example, also use in our lab causal biomarkers. So Albertine is a graduate student in the lab, developed. I mentioned one slide yesterday about this work, which is still under review. where we could enrich for CPG sites which are causal, kind of damaging sites versus adaptive sites, and apparently under certain interventions, under certain conditions, they perform better than any other clocks, but not under all conditions. So I think it's just an open question currently. Yeah, we simply don't know. Okay.
Yeah, to support that with some data is we performed a systematic review of existing clinical trials that are studying aging or aging-associated outcomes and using any of the clocks. So first, we saw that there are a lot of applications of epigenetic clocks, but surprisingly, a lot of them are using older generation, like Horvath 2013 clocks, and they were not designed to be used in clinical trials. So we also see that practice, it seems that they are going for the easiest, or it's not, that practice is not informed, and it could definitely be improved. But we also see now more metabolomic biomarkers being used because some believe that it's more interpretable. It's easier to interpret them. But overall, omic biomarkers are becoming among the most commonly used in aging and other cancer or other aging-associated disease studies for clinical trials.
I believe the path to getting a more causal biomarker is through modern AI, such as transformers. As you can see, the GPT chat program couldn't have the results that it has without a causal model underneath, as well as a lot of your visual neural networks. At Rejuve.ai, we're pulling that thread even more and looking at simulating nature more and pulling threads rather than designing a way towards cause through our generative cooperative network, which has many transformer models interacting with each other as human beings interact with each other and talk to each other, and through that come at better models of causation.
I would like to follow up on that, because I think AI is always being used as promise, and this is buzzword, right? And AI did like a lot of good things in the world of like in the digital world, on the Facebook, that like all your advertisements becoming better, and that was mainly possible because they had huge amount of data, and digital data is rather cheap and affordable. And if we look into biological data, is way more expensive to acquire, and it costs more money, and thereby a lot of the data sets are like much smaller, right? Even like most people in academia work on the same data sets that are public, and money has been spent. But do you think all those companies that currently work on promise like aging biomarkers to commercialize them, their data sets are not that large? Do they even capture like all the things of aging, and how valid are those for like the general population?
Well, if underneath the AI model can understand the language of biology, then it can take, one person's data, it's still a lot of data, and understand how the multi-omics integrate together. And then through a lot of data, it can make a foundation model, so that if you have a small amount of data, that large amount of data can be understood by the AI to help interpret the small amount. So that's the purpose of the transformer foundation model. And just having a lot of data helps it to understand the mapping between different omics.
Yeah, I kind of want to build off of that by giving an analogy from a different field, and then kind of posing a question, especially the kind of the biomarker consortium side of the house. Random example, like take something like video streaming or something like that. You might want to analyze for like a final trait, year-over-year retention or something like that. And in order to determine that, you might have these sub kind of markers, right? A cognitive marker, decision-making speed, this and that, a more personal characteristic, does a person have this kind of profile or that kind of profile, right? So there's this kind of hierarchy of markers. There's like the first level marker, like decision-making speed on the menu, but then that might all feed together into an aggregate, like decision-making cognitive marker. and then a different one for the personality type, and this and that. And then at the end, different kind of equations can be used to test, oh, well, it turns out that for year-over-year retention, this is a very simple example, 2 times this times the square root of that plus that turns out to be the most predictive thing, right? So my question is there work like that being done of saying, okay, in order to get a comprehensive, robust aging biomarker, we want a physiological metric which can have these 3 tributaries feeding into it to come up with a physiological metric, and then an epigenetics, which would be the Horvath clock, the Grimm age index, or anything like that? Is this kind of like tapestry building of hierarchies where then you can make different equations based on them to make an aggregate clock? Is anything like that happening that's analogous to the other case in tech?
With foundation modules, you have clustering into modules. And those modules are clusters of methylation CpG sites that together have meaning for the foundation model. And whereas I believe it's reasonable to take everything that humans have found to be of value and make a mathematical equation of that. The transformer is already making a mathematical equation of those modules underneath to get the predicted results that we just can't easily understand.
So before I kind of broaden it a little bit and start talking about how we can introduce biomarkers into the clinical landscape, I've just a question about one more specific biomarker, and I've been hearing about it years ago, and now everybody's focusing, obviously, because of the rigor, the methylation clocks and various omics approaches, proteomics and metabolomics, and looking at comprehensive patterns and correlating that with your biological age. But I remember some years back, people were focusing, particularly Elizabeth Blackburn, on telomere length, right? And how supposedly having various interventions could fluctuate the lengths of your telomeres and cause your telomeres to extend or contract, right, based on a variety of interventions, such as exercise. I'd like to know your thoughts on that, particularly since we haven't really been hearing about telomeres lately, at least myself for a while.
I just wouldn't use it. Because it's just one parameter. Like for the any clocks, it's select on many parameters. It's just one, and just length of telomeres simply doesn't correlate with anything. Because the rate of reduction does correlate, but again, it's just a very limited kind of data, limited information. I mean, it's useful as one of the small components of a larger kind of biomarker.
Yeah. We discussed about this a lot in our lab meetings, and I was showing the lab and Vadim last week that we already have 300 different theories of aging with 300 different definitions, and telomeres is one of them. And since aging is linked to everything, and almost everything in the body changes by aging, so there are a lot of candidates. And the other day we estimated that there is almost a new clock of aging coming every week. So now it's almost every few days. And there are also a lot of competitions. So this validation effort that's going on to cross-population validate a biomarker across many different populations is also a good movement to show if these biomarkers are generalizable, if they apply to different populations in different contexts. And the other thing would be the resolution and the predictive power. So telomeres, just one limitation is for every sample, you only have very few data points for telomeres. But compare that with epigenomics, you have 30 million data points for every single cell. So I don't think there is a fair competition over there.
Well, I would just like to ask a question. If you're having a competition for biomarkers, how do you know who won?
Yeah, so we are generating some data from hospitals that are collected, the samples are collected decades ago, and we already know the outcome for those people. But we can't release the data, we can't even share which hospitals, and the competition would be multi-phase, and the last phase, we internally apply those biomarkers on this data.
Okay, that's interesting.
Yeah, I really like that. In the machine learning world, a lot of competitions have helped a lot of breakthroughs. And I think hopefully we can put this dynamic into the biomarker space as well with the competition. So more competition we need, or more competitions we need.
I'll just second what Max said. I'm not a telomere expert, so I'm not going to speak out of turn.
So I'm intrigued what you said earlier, Mahdi, about biomarkers of aging being used in clinical trial applications, and then how some of them were an outdated version. What is the landscape, the regulatory landscape for incorporating specifically biomarkers for aging, in a clinical trial setting? Because after all, the FDA doesn't consider aging to be a disease. So what is the the endpoint that you're actually measuring as, with a biomarker for aging panel, right? So if it improves, obviously you can't wave that as proof that you've rolled back the clock or cured aging, right? There has to be some other disease parameter perhaps that this is being correlated with, not broadly speaking aging, but maybe something else. So I'd like to know a little bit more from the panelists on their views on how they see biomarkers of aging being incorporated into the clinical trial landscape, and then maybe even further beyond into the clinician's office, and how does it look now presently?
To me, the main question is kind of very fundamental question for us to understand what exactly we're measuring, what's the best way to measure, and only then go to FDA approval, because we currently don't have that understanding.
I'll jump in. So building on Vadim's point earlier, there's a million different definitions for aging, right? So it's hard to just say, well, what's the proxy metric for aging, right? But that doesn't prevent us from making just useful other definitions that are clinically relevant and maybe creating indications based on that. So I'm going to speak to this from the non-invasive physiological angle, because that's my expertise, right? But, you could, the NIA, I know people in the NIA have this concept of the deficit accumulation index, right? Functional things that can go wrong with you: walking gait disruption, loss of visual acuity, grip strength, degradation, etc. So you could make some kind of determination that's, if you have 30 of these deficits, you undergo an intervention, and now you have 20 of these deficits, there's been a reversal on whatever you want to call that. And that could be some kind of indication. That's just one example, but I just want to note that the amorphousness of aging doesn't necessarily have to pose a complete roadblock. I mean, not that there isn't difficulties in getting all this stuff to happen, but yeah.
So are there any trials that are to that end that anybody here is aware of, since you brought it up, that are using any type of biomarker of aging? It doesn't have to be a methylation clock, a variant, although that's probably the most accurate, that are using that as for a different indication for a particular disease of aging. So you give a treatment, you see, an improvement in cardiovascular health for a patient, right? So that's something that is accepted by the FDA. But of course, that also correlates with a more youthful state, perhaps, and that would be reflected in that type of biomarker. And of course there's other biomarkers that could be used to judge the health of, the health status of your cardiovascular system. But do you know of any efforts being made to correlate, a biomarker of aging per se, that we're talking about, with some sort of other indication that's a disease of aging, that can then be utilized in a clinical trial or a clinical setting?
Yeah, I think maybe Mahdi would answer if it's okay, because we actually studied the literature very extensively, specifically for that question, and compiled the list exactly to address that question. So.
Yeah, sure. So personally, I think we are still far from having that discussion with FDA. I started, Larry is here. I've been talking to Larry from FDA and attended their meeting, but we are still talking different languages, and it's a big gap that we need to cover for the next few years. But to use as a model, cancer is the field that is using biomarkers, these molecular biomarkers, very nicely. If you heard of GRAIL or other companies now, there are around 20 different companies that are focusing on molecular omic biomarkers, and they are having that discussion with FDA. They are already, some of these biomarkers are already covered by Medicare, so they are way ahead of us, and I think we can use that model. But one of these gaps is so there are different steps. The first one is to show these biomarkers are predictive of outcomes. And even methylation clocks, even the best ones, even GRIMAGE, the predictive performance that we see are not good enough comparing to biomarkers of cancers or these specific biomarkers of diseases that we can take that to FDA and start that discussion. So for us, the first step would be predictive biomarkers, having good enough predictive biomarkers, and the next step would be response biomarkers that would help to identify right interventions. So personally, I think we still have a few years and a lot more to cover.
Mahdi, could you just follow up? How big is the difference between the predictive biomarkers of cancer and aging, and aging clocks? Are we like 90% there? Are we 50% there?
The difference is a lot. So to give you an example, for cancer right now, we are at a sensitivity and specificity of 90%. So with 90% accuracy, we can say if the person has a tumor in the body. But for biomarkers of aging, there are a lot of challenges. First of all, what is the thing that you are predicting? Right now, a lot of these biomarkers are predicting time to death, but the accuracy is nowhere close to that, even for the easy ones for mortality.
I got a follow-up question based on that. So with cancer, right, you have kind of like a binary, right, like tumor is present or not. So what is factoring into that specificity? Is it within mean absolute error of 2 years or something? Like what's the condition for that accuracy?
Yeah, a lot of them are going for the existence of tumor anywhere in the body. So that's the binary outcome.
I mean, for the aging side.
For the aging, a lot of the current ones are going for mortality, say 10 year survival. In 10 years, if they are alive or dead. And the best one that we see are very far from biomarkers of other fields. And it's also reasonable because it's a much harder problem to work on, and we're still very early.
So I remember going to a TED conference a long time ago, or 10 years ago, and they had a camera and a computer screen, and you'd walk by it, and a little box would go over your head, right, on your face. It would track you digitally, and then the number would pop up over your head, and that software was predicting your age. And this was well over 10 years ago, and I remember walking. I'm like, I walked over there, boop, and my exact age. So maybe he was actually just doing facial recognition and pulled up my ID card and just did something funny like that, and it wasn't actually predicting my age. But I'm going to assume that it actually was doing what it was doing, and it impressed me. Of course, a data point of 1. So so this is something near and dear to Keith's heart, which is non-invasive digital biomarkers, and of course the opportunities, advantages are they're non-invasive, they're fast, right? You don't have to send out a sample for analysis. You don't have to do it. You just walk in front of something and it tells you, oh, you gained 10 years since last night. What did you do, right? So is anybody, so I'd like to ask the panelists here, what are your views on the applications and the state of the art of digital biomarkers, non-invasive digital biomarkers of aging, and how do you see that tying in with the intracellular biomarkers, the molecular biomarkers that we've been discussing and that we mostly discuss when we talk about biomarkers? So maybe we'll start with Keith.
Yeah, I guess I'll start this off. And that was actually a nice kind of follow-up to the question that I just asked Mahdi, right? Because some of these digital biomarkers, so some based on walking gait analysis, voice, face, and if I remember right, some of the let me back this up by saying that one of the qualities that you'd want a digital biomarker to have, not the only quality, but one of them is that it should be able to reasonably accurately detect the chronological age of someone who's not undergoing like a bizarre intervention, right? You want it to do more than that, but that's like a validator, right? And I believe some of these facial markers are, mean absolute error plus or minus 3 years on that, which is pretty decent, right? So that's why I'm personally optimistic that if we can combine a lot of these things, we might be able to get a purely non-invasive marker that at least ticks that box down to 1.5 years. And then this doesn't address the causative issues and all that kind of stuff, which is why these things need to be paired. But what I'm really optimistic is if, through the work of the consortium, et cetera, and other organizations working together, I'm hoping we'll see emerge from AI analysis, et cetera, interesting corollaries. I'm totally making this up, right? But like grip strength of all the physiological metrics seems to be remarkably correlated to the Horvath clock for some reason, et cetera, right? So you can kind of create this like quick and dirty signal of just like a non-invasive scan, and then if something is interesting now, okay, now you go in for the panel, right, of the deeper biomarkers. So that's the value I potentially see as part of that.
I think that part of the answer lies in AI's ability to do micro-macro integration. You can think of the omics level as being the micro level, and these clinical types of easy-to-see markers as being the macro level. And if you want to look at cause, then that is a good place to look in micro-macro integration, because emergence is what makes AI capable of finding cause. Like the emergent abilities of ChatGPT are what enable it to mix different scenarios together correctly, because it has a causal model underneath. And that's from emergence of the simulation of neurons.
Yeah, I mean, here's the thing. I mean, all those digital biomarkers that are like, we know is that there's some signal in there, right? I mean, like your gait speed definitely is like different when you're like a small girl running through the meadows, right? Versus if like you're an old man and you have like a third leg with your crutch, right? And they can pick that up. And I think they're good and cheap, but the thing is, how do we go back to biology from that as well, right? Because I think it's hard to come up with an intervention only on those digital biomarkers, right? So it's like, as we talked earlier, right? It has to be the combination of both, and like we have to look at from both ways, from the top, like from the macro and from the micro. And the thing is, given that the digital biomarkers are so cheap to collect, I think we should just definitely always collect them, right? In each clinical trial or in each study, because it's like just pennies in most cases, or like even like your phone, right? People have to, it's literally for free that they're being collected.
Yeah, I completely agree with Max, and I'm also split between a lab at Stanford who is doing digital biomarkers, Mike Snyder's lab, and it's all about measuring aging. And I personally believe digital biomarkers are perfect for measuring aging manifestations, but for understanding aging or the root causes of aging, that's where we need these molecular studies. And another thing that I believe that there is still not a good connection between those biological, those very advanced deep learning model based on these digital biomarkers and measures, and those root causes of aging. And one reason is it's a very interdisciplinary field, and we need this kind of discussion to have with people who are building these neural net models and talk to them about biology and to learn from them. So it's a very interdisciplinary, two advanced fields that need to be connected.
I also like the development of digital biomarkers and facial recognition kind of biomarkers, because they, like omics methods, they are integrative methods. So, which is, aging is a systemic process. Therefore, we need to see this as emergent property in a way. So, as often mentioned, organism is more than the sum of its parts. And therefore, perhaps a biomarker that would assess the age of the organism does not exist yet. But still, these digital biomarkers plus omics kind of move in the right direction.
Yeah, so I'm interested definitely in correlating the variety of biomarkers and making sure that they all correlate with one another. I remember reading an article, I'm not going to say who it was, but it was somebody who was basically doing a variety of interventions and saying, and they were applying a variety of methylation clocks and probably some other cellular biomarkers and saying, I think they were in their 60s, and they said, well, I'm actually really, I'm biologically 30. And I looked at the picture and I said, no, you're not. You know, so there's clearly a disconnect there between the physiology of this individual and what the molecular data was presenting. So I guess a question I have is, and perhaps people are looking into this already, and you can fill me in if they are, is that are there, so when you do an intervention and you roll back the clock, are people looking at if there's a lag between a change in a biomarker and a physiological change, right? Because obviously if you go on a diet, it takes some time before you lose weight, right? You don't see the effect immediately. Although if you take a certain, transcriptomic assay and you give an intervention, all of a sudden you might see the clock rolled back, right? But there might be a lag, I don't know, before you actually see actual benefits. That could take hours, could take days, could take months, before your other biomarker, your digital biomarker could, that maybe you're looking at gait, can kick in and say, you're now finally 20 years younger, even though the other clock, said you were 20 immediately. I just want to open the floor to thoughts on this, if people are making correlations like this and considering this when they're looking at a variety of biomarkers.
So I can't answer the question about the time delay lag, which is interesting, but you just made me think of another potential confounding factor here is one of the things that we're going to have to suss out at some point is whether the effect that we might see on functional age is due to some systemic change or due to changes in lifestyle due to the intervention, like, I suddenly become more active, et cetera, et cetera, et cetera. So that's another confounding factor. I realize that I don't know if there's work being done to kind of tease out those two things, and that's something where I think a combination of biomarkers could tease out where if I'm not achieving gait or whatever improvements, but I am achieving molecular improvements, then that would kind of rule out, you would think, it's just because I'm on uppers or something like that, right? Yeah.
I think you have multiple research studying that with parabiosis and stress, so you know more about the timing.
Yeah, I mean, it's a difficult question. How do we assess rejuvenation? Because the way I think is the direction from the young to old is not the same as from old to young. The changes we cannot simply reverse. We could reverse some aspects of aging, and so, but it's not exactly reversal. It's not exactly the opposite kind of direction. So for that, we need special biomarkers that would reflect rejuvenation. So currently, the way we do it is that we just apply many biomarkers. So, for example, if you work in clocks, we apply, RBS-based biomarkers, but also a lot of Steve mentioned that today there's a beautiful paper just published in Science and Nature Aging just yesterday. Actually, this clock 2 and clock 3 extremely useful. So we currently apply them, but in terms of rejuvenation, for example, in case of parabiosis, we see the effect on this clock 2, clock 3, RBS-based clocks, transcriptomic clocks, and we see, okay, this must be rejuvenation. But sometimes it's unclear. Some clocks show there is an effect, sometimes not, and it's very hard to interpret. So there are some extreme cases of rejuvenation, like we convert somatic cells to iPS cells. I mean, clearly they're young, but many clocks report that. It's more tricky in the case of partial reprogramming. Sometimes it works, sometimes it's not. We also have case of rejuvenation during embryogenesis. That's also most of the clocks show this, both transcriptomic and epigenetic. But again, so often in the kind of lab setting or clinical setting, we observe relatively small effects. And with existing biomarkers, it's just tricky to figure out whether there's true rejuvenation or not.
Yeah, I agree with that. Oliver, it might be time for questions in a second, but before that, I want to ask a question from the audience. But I want to ask a funny question to the panel first as the last question. Are there any unforeseen implications of having accurate biomarkers for age? Because here's a funny story. I think I'm remembering accurately. Like 2 years ago or something, there was a case like someone brought someone to civil court because they lied about their age on their Tinder profile. Right? But then the defense the person used was, well, I feel 25, so I put 25. But what if there's a future where it's like, my Horvath clock says I'm 25? You know, is there anything like that that you think is like we haven't thought of that like might be a downstream effect of having this? Nothing.
That's a societal and legal question. But yes, we did talk about this a while back when and of course the news media brushed it aside as this is like complete ridiculousness, and coming from an aging research background, I'm like, no, it's not. It's actually a great question. Like, what's more important, your age on your birth certificate or your biological age? I would say your biological age, right? So, and our society is not structured to deal with that. So,
you remind me of some of the problem with the first generation methylation clocks. Using AI with a goal of chronological age. And if the AI were to be perfect at its goal, then it would be useless because we already know their chronological age. So you have to train the AI on something besides their chronological age. And thus the second and third generation clocks where they looked at chronic conditions and is that really age as such? So it's a little complicated.
So going back to the more fundamental question before we take questions from the audience of chronological versus biological age, I was just thinking about this. How do you initially make, and maybe Steve can chime in, how do you make this, which data set do you use to establish the biological age? Because, right, you have to rely obviously on a data set, meaning the population. You're taking population samples and saying, okay, well, this is, and then take an average, right, and say that this is what the methylation state looks like, or whatever your other biomarker is for a 20-year-old, a 21-year-old, a 25-year-old, 30-year-old, right? But of course, the population matters, right? So if you have a, super healthy clonal, population, living somewhere, then you should have a complete one-to-one correlation between chronological and biological, right? But if your population is really living next to some radioactive wasteland, right, then that's going to throw things off. And of course, we're all very heterogeneous, so it depends who you're actually putting into this data set. Yeah, that's my question. How do you ensure that there's no bias of this sort coming in, and taking into consideration also different genetic backgrounds from individuals, or do we just cast a wide net and hope that that's sufficient?
Good point. So, I mean, depends on the population. So we could, in our lab, actually, we deal primarily with animals. So it's very easy because Black 6 background in mice, genetically identical animals in the same condition. So this kind of eliminates that issue. But in the human population, you're right. Some population would seem older than others, based on these measures.
Yeah, exactly. To answer that, with the help of Steve and Luigi Ferrucci and all the people who helped with the first work of the consortium, now we are working on cross-population validation of existing biomarkers. And we identified all the cohort studies, and some of these cohorts are a few 100,000 people. So now we are talking about some of these biomarkers that have been tested and validated across many diverse populations, from Asia to Europe to American populations, and how we can move that forward. So the good news is some of these biomarkers, omic biomarkers in particular, are performing as well across very diverse population. But the catch is that these are tested mostly on first world population. So we don't know if they are true for all human or mostly for advanced countries. But that's the state we are at now.
So kind of a quick follow-up question. Is there a temporal element in this as well? Because one example that I'll give is I read a while back where the average body temperature is 37.5 degrees Celsius or 98.6. And that was a measurement taken a long time ago, and that's been used as a reference. And then relatively recently, they did another study and tested individuals and found out that no, it's actually a little bit lower the average body temperature, maybe by, I think, about 1 degree, something quite significant. And I don't know if they resolved the speculation as to why, but one of the reasons that people were speculating why it was higher in the past was not because there was errors, but perhaps people were more prone to infections and fevers, so people had generally a higher body temperature to begin with. And that changed over time, right? So if you have a population and you're getting these data points now, and maybe 20 years from now, everybody's living a healthier lifespan, then are people taking into consideration that you have to keep adjusting these clocks to take into consideration changes in the population over time, not just the snapshot of heterogeneity now at the moment, but heterogeneity throughout time as well?
Yeah, I'll answer quickly. That's actually a really great point, Oliver, that I don't think is often thought about. It's a moving target, right? So I think to bring it back to the theme of this event, this is where decentralization becomes important, right? Where you can create systems for accumulating data from diverse populations longitudinally, consistently, et cetera. Now, obviously, that's going to require a lot of infrastructure, et cetera, but I think that is part of the mission of true decentralized science, is creating those apparatuses to mitigate these issues as best as possible.
Okay, well, we do have some extra time because of, so right now I'm going to pass the mic over. I think we have somebody in the back with a mic for questions, and I see a bunch of hands up, so.
I also asked a question during Dr. Horvath's talk, and I tried to suggest that maybe different organ systems were moving at different rates. I just worry about this like regression to the mean of people. Like, what if people age in different ways? For example, some people might be more prone to DNA accumulation and they have their specific sets, but some people might have something like a stem cell depletion sort of aging phenotype, and then they might be really hard to deal with, so because they're very rare cells and they're quiescent, so you might not even be producing biomarkers while they're actually a large driver. So this is just my like one concern, like maybe there is no holy grail single thing. How do we talk about these like fringe things? And I guess I also have a question too. Why do we always define it as markers of aging and not markers of youth? Why are there no youngness markers? Because kind of, I think you can have like this bivalent state where you have certain youthful pathways that are active and also certain pathways that are more age engaged. Like, how do you maybe incorporate that sort of a signal so somebody could be simultaneously old in ways and simultaneously young in ways?
Yeah, I'll take the second part of that question and I'll leave the first part over to the other side. That's exactly the reason why I think that my personal opinion is that we shouldn't necessarily get hung up on calling it a biomarker of age or whatever, because you might pull in some like, other conditions like, oh, people are think you're ageist or something like that, where I think that's important to come up with proxy metrics that say something very specific. So to your point, like, are you functional? Can you do these things? Like, that kind of thing, and you can call it the functional clock or something like that, right? Anyway, over to you guys for the other part of the question.
Yeah, I have a quick answer for the first question. The good news is that there are some research labs that are working on ageotyping, and it's a different approach than biomarkers of aging itself that goes toward the average, but ageotype is clustering people into different ways of aging. There are already good results. If you can take a look at ageotype from the Snyder Lab, it published in Nature a few years ago, and they are continuing that work. But those are also harder questions because you need larger population and more advanced machine learning, unsupervised learning.
But I agree with this, but at the same time, different parts of the organism, they don't age in separation from the other parts of the organism. They all influence each other resulting in a kind of organismal aging state in a way. So this is something really exciting kind of to find out how exactly this happens, but we observe this from some existing experiments where, for example, do organ transplantation, and interestingly, organ kind of interacts, heterochronic interacts really with the body in a very interesting way in kind of the jointly age in a common kind of joint way. So yes, there are ageotypes and some organisms they have some of the systems that age faster, but at the same time, it's in a way it's compensated by the other systems.
We have all these sort of different... I'm just saying I think humans might be especially prone to aging in different ways because of the different roles we have in society and the different, external effects. So we might actually see these unsynchronized and sort of misleading symptoms or signifiers, or maybe they are indicative. I don't know if they're misleading or not.
Yeah, to echo some of the earlier points, this is why I think it's important to have like a panel of very different types of biomarkers all going at the same time, so you can try to normalize for some of that.
And the other side of that is there are also common roots of aging of all the tissues and all the cells and all the mammals that we could also study those.
So I have a question actually. I think you all have already talked about it. Like if they're twins who happen to be living in entirely different circumstances for whatever reason, and at their 40th age, if you look at them, they age differently, right? I mean, their circumstances, their genetics may be the same, but they age differently. So my question is, which you were talking about, in all the conversations that you had. But my question is, because collecting the data is so difficult, collecting, understanding diversity is so different in circumstances of people, an approach could be that one hospital has a certain approach of healing, if healing was to be understood as a quality of life, right? So if one particular hospital deals with their patients of same symptoms in a certain way for healing versus another, do you have any data of that sort to understand what is a better way of, how could you have a biomarker within a society or within institution or something like that? I was just curious.
That's a hard one, huh? So I started talking to a lot of people who do population studies at a larger scale. So Andrew Meyer from Singapore. We also invited someone from WHO in our panel for the first work to define aging. And regarding to the other point, why we say biomarkers of aging and not biomarkers of youth, simply because it's just easier. But I understand that there's a lot of negative aspects of it. So we started by writing a page that we should have biomarkers of health and biomarkers of vitality and intrinsic capacity, all these good terms that WHO people and UN people came up to study societal aging. But it's just, we are not, basic biology is not at the point that we can incorporate that into our research. So hopefully with more time, that becomes better.
We have time for one more question. And don't worry, if your questions aren't answered, the panelists will still be here. Conference is still going on, so you can talk to them one-on-one.
Sorry, just wondering, I have the mic here. Just wondering if there's anything akin to an aging trajectory that people look over large data sets. So if you in a particular population, people die and regress back from that and look at how often they go to the hospital, how often they are sick, what they're different, over a large scale population. And you plot out an aging trajectory and you look at interventions. If the purpose of this aging clock business is to see whether we have something to measure the impact of interventions, if you then can take 10% of that large population and look at an intervention and its impact on the aging trajectory, which would be how many times do they pick up an infection, how many times do they visit the doctor, do they have a fall, do they break, etc., back through their age. I guess it would be irrelevant for younger ages, but particularly for the older age. Is there anyone doing anything of that scale to assist with this process?
I'll leave the actual question of whether you guys are doing that up to you. One thing that I'll say that's interesting about that is, something I've talked with Oliver a lot, is in addition to just your biological age versus your chronological age, there's the trajectory, like you're saying, and what the curve of that looks like, right? That also made me think of another thing that I'm curious if work is being done. If there is an intervention that can do something to affect, I know there's a lot of things right now that can affect the Horvath clock to some degree. It's interesting, it would be interesting to see over repeated doses of that, is the perturbation of the Horvath clock consistent each time, or do you get diminishing returns every time? So I'm answering your question with another question. are things like this being looked at, or right now it's just trying to get an accurate, timestamp of biological age versus chronological age first before any of this stuff?
That reminds me of a slide that Vadim has in his slides about 10 challenges with biomarkers of aging, and now we have 11.
All right, awesome. Well, I'd like to thank all of our panelists, and thank you, audience members, for all the questions you had. So we're going to set the stage up now for our next speaker. Thank you, everyone.